the physics question that was posed at the beginning when we started talking about limits. So it has to do with relativistic mass, the relationship between relativistic mass and rest mass. What you find in physics is that when you talk about relativistic physics, what's that mean? You know? It's relativistic physics. It deals with the physics of kind of extremes, right? So we're talking about special relativity, like as we are here. We're talking about at very high speeds. So as your speed increases relative to some reference frame, strange things happen. It really does. This isn't just, physics really works this way. Objects that are moving at high speed, like if a car were to drive at really high speed through the room, not just sort of high speed, but significant percentage of the speed of light, you would notice that it would be Lorentz contracted, its length would shorten up, and it really would happen. It would be compressed along the direction it moves from our perspective. Its clock would run slowly, so if the driver were holding out a clock as he was driving by, you would see the time passing very, very slowly. And you would notice that its mass or its energy would increase. So this deals with the relativistic mass. Here's the equation that we use to describe relativistic mass. So M stands for relativistic mass, M naught is the rest mass, V is speed, and C is the speed of light. It's the constant speed of light. So what happens when, oftentimes in these science fiction movies, people travel faster than the speed of light. And the only way, there's some possible, they're not probably realistic, but there are some ways you could sidestep that, the speed of light. But this tells us something. If you're literally to travel from point A to point B through space, this tells us something pretty important about the way the universe works. How would we want to explain or use this mathematical model to illustrate or to explore how fast an object could go? Like, what if we wanted to push up against the speed of light? Like if we want to calculate the relativistic mass for 0.5 c, it's just a formula, isn't it? I would just plug in for my v. That's the only variable here. Everything else is a constant. The rest mass is just the mass of an object at rest. That's constant. It's not going to change in the course of this example we're looking at. Speed of light is fixed. It's about 3.0 times 10 to the 8 meters per second. So that's also fixed. The only thing that can change is v. So really this is a function of v. If I want to plug in a velocity or speed that's 0.5 c, I could just plug that in here and I would get an answer. Okay? We could see what that is. And we'll put it in Desmos in a second, maybe, and look at a graph of this. We could put in a value of 0.9 c. But when we try to put in c, if we try to evaluate this function at c, what happens? I want to plug in c, the actual speed of light for my speed. I'm dividing by 0, right? Now, what we say the other day about limits, there's only 3 kinds of things that can happen. Right? Either you're going to get an answer that works, which would be the case if we put in 0.5 c. We're just going to get some number coming. It's actually going to be some number times m naught, some percentage of the rest mass. It's going to be a little bigger than 1, okay? But when I try to put in c, I get the second kind of result. I get an answer which is some number by rest mass, whatever that is, it's some constant divided by 0. So some number, some non-zero number divided by 0, we said is just, at this point, is just a does not exist situation, right? And then the third one would be indeterminate, 0 over 0, which we don't see here. How could we deal with that in this case? It's not indeterminate, and so we can't do any magic algebra to make this thing work out. So what could we do? Any ideas? Like if I wanted to take maybe a limit, right? Because we can't actually, if I try to plug in c for v, I get something that doesn't exist. So this function is not defined for that value of v. But maybe we could explore what's going on by taking a limit, right? Because because in the case of a limit, we never actually get there. And so we're not stepping into that singularity in the function where it doesn't exist, right? So how could we structure that? The limit of my relativistic mass as c does what? Okay, as c approaches v. Now, we might even need to be a little more specific than that. From which direction? From the left, from values of v that are less than c. Because we're going to say accelerate from 0 up to the speed of light. Yes, sir.
Should it be v as v
Oh, sorry,
approaches
v approaches c. No, you're
okay,
right.
I was
You're right. My mistake. As v
Right,
approaches
C is the
c
constant.
from the left. Yeah, c is the constant. Good. Okay. And as we do that, what do you think is going to happen here? And this is kind of a challenging question. We're not totally equipped to deal with this, but it sort of propels us into some things we're going to talk about after roundup. But at least it gets you thinking about it. It's an interesting question. So if I take that limit, what's that look like? If I take that limit, I end up getting something like m naught on the top, and on the bottom, I've got the square root of 1 minus what? What's that going to look like? If I take a number slightly less than c, and I divide it by c, what's that look like? Like what would 0.999999999, etc. divided by 1? A number just under 1, right? It's not 1, but it's pushing up to 1, isn't it? And what we could do here to make things maybe a little bit more convenient, let's v squared over c squared using properties of exponents. Couldn't I just write that as the quantity v over c squared?
Yeah.
Okay. So then that number here, v over c, it looks like it's trying to be 1, but it's not. Well, here's a way to think about that. That number is the same thing as what we might call 1 minus. Okay. You understand what that means? 1 minus is a number that's to the left of 1, but it's arbitrarily close, as close as you want to get, right? So it's butting up to 1, but it's not. It's less than 1. It's any number that's less than 1, however close you want to get to 1. Well, what is 1 minus, this is going to be confusing to say, 1 minus that special number that we called 1 minus equal to? What is that difference? A number that's exactly equal to 1 minus 1 that's slightly less than 1. So it's going to be, say it again, slightly above 0. So why not call that 0 plus? Okay. So we end up then with an answer that looks like m naught divided by the square root of 0 plus. And once again, what does 0 plus mean? It just means some vanishingly small but existent positive number, right? Well, what's the square root of a very, very, very small positive number? Small positive number, right? And it's actually going to be a little bit bigger, isn't it? Because the square root of 1/4 is 1/2. But who cares? If this number is vanishingly small, so is its square root, right? So we end up with a number like m naught divided by 0 plus. Well, what's that equal to, you think? If I take a constant divided by a vanishingly small positive number, what are we approaching there? Infinity, right? Does that make sense? I mean, as you let this number go closer and closer to 0 on the bottom, still being positive, the quotient is just going to get bigger and bigger and bigger in a positive direction, isn't it? And so what we end up with is positive infinity. So what's the problem? Why can't any object travel at the speed of light? Any object that has mass, that has rest mass?
It can't.
Yeah, because you can't push an object that has infinite mass. It would require infinite energy to make that particle go close to the speed of light, right? Like I don't know what the exact specifics are. I mean, now CERN would be the reference standard for accelerators, but CERN, CERN in straddles, it's what, Switzerland, France, straddles a bunch of different countries in Europe, right? It's right on the border, and it's the biggest particle accelerator in the world. It accelerates larger particles. When I say larger, I mean they're still really small. But there were some old, like at Stanford, this Stanford Linear Accelerator specializes in accelerating electrons. And so I think it's actually got the speed record still because it accelerates such small particles. But when you accelerate SLAC, it's this about 3-mile long building, and it's just lined with all these superconducting magnets that create this enormous field. And when you pulse that thing, the energy consumption is greater than the rest of the Bay Area combined is invested in this little packet of electrons. These are electrons, and these things are tiny. And you get these electrons to go 99.9999997% the speed of light, so they're going really fast. But even then, they don't go the speed of light, do they? Right? I mean, all those resources invested in this tiny little stream of these vanishingly small particles, but they could never ever go the speed of light, right? Because of this math right here. Because of what this limit tells us. It would require an infinite amount of energy, and that is not available, right? Okay. Okay, so let's get down to something a little more concrete. What about a problem like this? Tell me what you know about this. This kind of relates back to what we talked about yesterday.
Plug the one in for X to see what happens.
Okay, so if I try to directly evaluate, what do I get?
0.
0 over 0, which means more work, right? It's indeterminate, so we got to do something. All right, so what's your approach here? Does anybody know how to factor x to the 5th minus 1? I know, right? That's not a factoring pattern that you've ever studied, right? But there's a workaround here. We don't have to know that factoring pattern. This is a real challenging question, but I want to see if you can, today's a challenge day. Can we come up with a way to maybe deal with this? If I try to evaluate it, it's 0 over 0. Okay. Any suggestions?
You should just do X times X times X.
Well, x to the 5th minus 1, it's not anything repetitive like that. It's just a polynomial, right? But what do you know? I don't want to steer you too much. I want to see if you can come up with this. What?
X minus 1 has to be on top.
Say that again?
X minus 1 has to be on top.
Okay, so the x minus 1 factor has to cancel out. That's what I like to call sometimes the offending factor, right? You know that there has to be, eventually, when all the algebra dust settles, I'm going to have to be able to cancel out the factors x minus 1 at the top and bottom to get an answer, right? And this is a function that it has a hole. We know it has a hole because it's a 0 over 0 function, right? So it's got to exist everywhere except at 1, and that's how we get that indeterminacy to vanish, is to algebraically cancel those factors. So would you agree that I could write something like this on the top? I know it's got to look something like that, right? X minus 1 times something. Agreed? Okay, be clever. How could I figure out what the something is? And this is pre-calculus stuff. This isn't anything fancy. What can I do? Suggestion? By that question mark, what do I mean? Just some other factor that's being multiplied by x minus 1, right? Okay? There you go. Why not do synthetic division? Great idea.
Oh.
Right? Does that make sense? If I want to know what this other factor is, I would just divide x to the 5th minus 1 by the factor x minus 1, right?
Yeah.
Synthetically, that's easy to do, isn't it? Right? So if we did something like, let's simplify that. Well, there's the quotient right there. So if we do this synthetically, what do we get? What's the 0 that sits outside the bracket? 1. What are my coefficients? 1, 0, there you go. What do we know the remainder has to be? Okay. It's gotta be zero, right? It's gotta be zero. We know that x minus one has to be a factor of x to the fifth minus one, doesn't it? Right. Okay, so then, if we do the math here, we drop this guy down, right? I'm gonna get one,
One.
what do you know? Okay. So we find then that we could write this as the limit of x minus one, whoops, times all that stuff, right? So what is that? That's my constant coefficient of x, x squared, x cubed, x to the fourth. Right?
Yeah.
Do I see that?
Yeah.
So algebraically, we can cancel the x minus ones and we create a new function where we fill in the hole. And if we evaluate this function at 1, what do we get? 5. How about that? That's pretty cool. Okay. All right, good thinking. That was good. So I'll show you some